It's important to be able to tell whether a graph is the graph of a function or the graph of some equation which does not translate to a function. And later in calculus we're going to, we first study differentiation, and then we'll study implicit differentiation, which will allow us to compute derivatives at points on graphs of equations which are not graphs of functions. So it's important to know the difference between graphs of functions and graphs of equations that are not graphs of functions. Remember, the defining characteristic of a function is that for every point in its domain we get exactly one point corresponding to that point in the range. And quite often we have a formula to figure out what that point in the range is. We just plug the point x in the domain into the formula to find the unique corresponding point in the range. So this translates to a geometric property of graphs, and namely that for every x value in the domain, there's a unique corresponding y value on the graph. And that's equivalent to saying that a vertical line of the form x equals a cuts the graph of y equals f of x if it cuts the graph, that is, if x is in the domain, or a is in the domain, then it cuts it exactly once. And of course, the line x equals a, where a is not in the domain, doesn't cut the graph at all, because there will be no point with x equals a on the graph. So this algebraic property of a function translates to the above geometric property, and this characterizes the graph of a function, and this is called the vertical line property. So a curve in the xy plane is the graph of a function if and only if no vertical line intersects the curve more than once. That is, a vertical line might not intersect the curve at all, but if it does intersect the curve, then it's exactly once. So a vertical line cannot intersect the curve twice or more. So remember, when we talked about graphs of equations, when you have an equation in x and y, the graph is the set of all points x, y which satisfy the equation. So for example, if the equation is x squared plus y squared equals 1, the graph is this unit circle. And if you can look at the equation and solve for y uniquely in terms of x, then you can rearrange the equation to look like this. Y equals some formula in x, and then you get that this equation describes the graph of a function. So being able to solve for y uniquely in terms of x is the algebraic equivalent of the graph of the equation being the graph of a function. And so of course this is equivalent to the graph of the equation having the vertical line property. So to check if you're given a graph and you want to figure out whether it's the graph of a function or not, you may not be able to find a formula for the function, but you can figure out whether it's the graph of a function pretty easily with something called the vertical line test, which is based on this geometric property of the graphs of functions. So the graph of an equation is the graph of a function if no vertical line cuts the curve more than once. A vertical line might not cut it at all, or it might cut it exactly once, but not cutting it at all is allowed. But if it cuts it more than once, twice or more, then it's not the graph of a function. So this also applies to graphs given in pieces. Piecewise defined graphs are the graphs of several curves. And of course, as you know, with piecewise defined functions, the chances of getting a unique equation of the form y equals f of x, or a unique formula to describe the function, is highly unlikely. So you can apply this test without actually finding a formula for the particular function involved. Let's try it on 3 graphs. This curve, you probably, let me zoom in on the formula there. This is the formula. It's pretty complicated, and it's called the bouncing wagon curve for obvious reasons. And the question is, could you possibly solve for y in terms of x, uniquely in terms of x, in this equation? And the answer is no. This is not the graph of a function. It's not the graph of a function. And in particular, it's not the graph of something of the form y equals f of x. So it's not the graph of a function. And why is that true? Because it doesn't pass the vertical line test. So if I draw the vertical lines here, there's no problem. They only cut the graph exactly once. But if I draw a vertical line somewhere here, you can see this one cuts the graph 3, maybe 4 times there. So that's a no-no. So this one does not pass the vertical line test. In particular, I have found a vertical line here which cuts this graph more than once. So most certainly this is not the graph of a function. Here we have another graph, and when we apply the vertical line test, we see that it doesn't pass the vertical line test, because here we've drawn 2 lines, both of which cut the graph twice. So this is not the graph of a function. And in particular, you can't solve for y uniquely in terms of x here, but also you can't get a piecewise description of this. It's not a function. This third graph has a pretty complicated equation, so algebraically trying to solve for y in terms of x here would be rather difficult, but you can see from the graph that it does pass the vertical line test, at least close to the origin. The vertical lines, any vertical line that we draw here, cuts the graph exactly once. Now, of course, we do have incomplete information from the graph here, because anything might happen outside this range of x's and y's that we've drawn on our computer, but close to the origin in this square, it passes the vertical line test. Let's assume that this function carries on in this particular manner to infinity and beyond, and that's something you can check using calculus later on. So this is the graph of a function, if not in the overall picture, most certainly in this local area. It is the graph of some function. Now, of course, finding a description of that function either as a piecewise curve or as in the form y equals f of x is a hugely more difficult problem. Now we know that this circle x squared plus y squared equals 25, this is a circle of radius 5, and this certainly doesn't pass the vertical line test, so most certainly this is not the graph of a function. And what happens when we try to solve for y in terms of x here? We get y squared equals 25 minus x squared, and we can't solve for y uniquely. We get 2 formulas. We get y equals the square root of 25 minus x squared, and y equals minus the square root of 25 minus x squared are both solutions. So for any given x between minus 5 and 5, we get two different y's associated to it. Now, of course, these two equations on their own both describe functions, and when you graph them, what you get for y equals plus the square root of 25 minus x squared is this upper half circle, and that is the graph of a function, because we have a formula for y in terms of x, and so it should pass the vertical line test, and it does indeed. Vertical lines outside of the range minus 5 to 5 don't cut the graph at all, but that's not a problem. But any vertical line between minus 5 and 5 cuts the graph exactly once. And the other equation, y equals minus the square root of 25 minus x squared, gives us the bottom half of the circle, it gives us the negative y's, and that too is a function which passes the vertical line test.